Hello, everyone. Glad to see that at least 14 of you are here so far. So the idea for today's lecture is to do something a bit different. The original idea was to actually close the course with this, so to give you a sort of overview on the applications of 3D modeling. So just a brief series of applications, mostly a collection of previous master theses that others have done. But since Francesca, who is more of a BIM expert, is only available to teach you about BIM on Wednesday, so we will be closing with that instead. So I think you will find also Wednesday's lesson interesting. It will be more of an interactive thing with some activities looking at different BIM models. So I hope you can attend that too. So without anything further, let's have a look at today's lesson. So we will be looking today at a few different things. I mostly want to present to you 4 previous master theses from Geomatics, from students who did very good and very interesting work that is related to this course. But first of all, let's start with an overview. So as we have seen throughout the course, there are a whole lot of series of different kinds of representation that you can use to store 3D data, to process 3D data, and to do different applications. As we remarked at the beginning, there is no perfect representation that works for every single application. Each one has its own strengths and weaknesses, like we saw with 2 very sort of distinctive examples. Like on one hand, you have these point clouds that have very raw data that comes there mostly directly from the sensor, and it's not very structured, so it's very hard to do some kinds of applications directly on top of that. But you also preserve basically all of the input data, so you have things like trees and anything else that would be lost in most 3D city models. So most of the applications you will see are more based on this sort of semantic meshes, like the sort of thing you see in CityGML or CityJSON, because it's easier to work with in terms of applications. In this slide, you can see a few different examples. So if you have something like a 3D city model, you can do like visibility analysis, things like if you are looking out the window of a house that will be built in the future, what will you be able to see? In some countries, this can be very, very important. Like in Japan, they do these sort of studies to see, like when they build a new high-rise tower of apartments, what landmarks will you be able to see? And depending on that, the value of an apartment can change a lot, like just from a few stories down to a few stories up, if you're able to see some things that you wouldn't be able to see. Another interesting application is doing like energy demand estimation. Things like what is the energy efficiency of a house, how much heat will be dissipated, whether it's worth to do a retrofit of existing houses or not, like based on how energy efficient they are and how much it would cost. You can estimate shadows, so based on the position of the sun, you can see whether other buildings would get enough sunlight. Like in the city of The Hague, there is a municipal regulation that says that at a certain point, like 1.5 meters on a given facade, you need to be able to get a certain amount of sunlight on 2 specific days of the year. And this is to ensure that you get some sort of enough sunlight throughout the year. Utility management, when you also model things like pipes and wires that are underground. You can do solar potential estimation, whether it's worth it to install solar panels or not. Infrastructure, if you also model things like roads, railways. So I want to show you a few sort of vague examples. Most of these come from the thesis of Philip Bilieski, which was a colleague of mine. Yeah, this is an example, maybe based on flood modeling. So if you have a 3D city model, you can see what sort of things could be submerged or not. This can be done very quickly just by computing a plane, or it can be done much more realistically by looking at water flows and whether obstacles would be in the water. You can do, as I said, like noise modeling. So this is an example, like if you want to build a new tram line, how much noise would there be in the surrounding buildings? Like there are regulations now in the Netherlands in the environmental law that try to measure this, also to regulate it. You can do, this is the solar potential estimation, so how much sunlight you get in the different places depending on the angle of the roof. This is just a very simple calculation that takes into account the angle, but more sophisticated analysis look at where shadows would be cast from neighboring buildings. So if you have a high-rise building next to you, you might not be able to get a lot of sunlight for your solar panels. And yeah, this is also the example of visibility, like from a given window, what are you able to see or not? Yeah, I already mentioned to you some of these applications. Other things you can think of are more based on visualization. Visualization of 3D city models is used a lot, like for gaming. You have seen maybe things about what the Microsoft Flight Simulator is able to do nowadays with realistic 3D cities. There's a lot of virtual tourism now, especially because of the pandemic. You can do realistic navigation. Like now there's an AR mode in certain cities when you use Google Maps, where you are able to see exactly what would you be able to see if you went to the place, which is useful in order to pinpoint your way, especially in dense cities. Yeah, people also do like computational fluid dynamics. There's a course that will be given by Clara in the next academic year about that. So you can model wind speeds around buildings, which is useful for things like air quality, like how much pollution you get based on the spread, what is the effect on buildings, like whether the wind creates some sort of stress on the buildings, and the rest I think I mentioned already. So for most of today's lesson, I actually want to talk to you about 4 MSc theses done by previous geomatics students. Maybe this gives you a bit of a sample of things that you can do. And if you're really interested in this sort of thing, you can contact us for a potential thesis topic. We're happy to talk about that. And yeah, as usual, if you have any questions, just post something in the Twitch or in the Discord chat and I'll answer right away. The first master thesis I want to talk to you about is by Roland Bouters. This is from quite a few years back, but it has been very useful and has a very interesting result. So the idea is that it's easy to create 3D models of the exterior of buildings just from things like LiDAR data plus some sort of base map. But creating indoor models is very difficult, and when you look at 3D city models in practice, you see that usually there's no indoor data available at all. And also when you look at CityGML, at least in version 2, you have this LOD4 for interiors, but it means that you cannot model interiors except at very, very high detail. And the idea of this thesis was to do 2 things: to define a sort of basic interior representation that just models stories, which is useful for some applications, and also to generate these automatically by looking at the exterior geometry plus a very simple attribute that says how many stories you have, and to use this to compute the net internal area, which is used in the Netherlands for taxation, for instance. I will explain this in a bit more detail later. So the first part was this definition of an basic interior level of detail. So on the left you can see what is the LOD2 in CityGML or CityJSON. So this sort of simple exterior of the building, but with a correct roof shape and so on. And Ruland actually defined what was called an LOD2 plus, so a similarly simple representation of the interior geometry of each story. And these two can be combined together, as you see on the right. The idea is that to make them fit also with each other. In the Netherlands and in many countries, you can get an indication of where stories begin and end just by looking at the geometry, because usually when you have the eaves of the roof, they tell you that the story begins exactly at that point. The same can apply, for instance, to balconies, because balconies are not in the middle of a story. You enter the balcony and the bottom of the balcony is at ground level, at level of the bottom of the story. So even the exterior geometry can tell you a lot about where stories begin and end. This is another example. So like there's an extension of a story in the bottom, and this tells you that most likely the ground floor extends all the way up to that part, and then the next floor up is a bit smaller. So Ruland used these kinds of heuristics plus doing some snapping, like you divide the vertical length of a building equally, and then you try to snap a bit these values to the places where you have indication where a story should begin or end. And he also looked at what could be the potential thickness of the walls. He examined these architectural models that are stored in the municipalities for building permits, and he came up with some good values based on the kind of building, when it was built, and so on. That tells you how thick the walls usually are. There are two values that you can see here. One is for shared walls and one is for exterior walls, which tend to be a bit different in some cases. And once you know where each story should begin and end, like vertically, you can do Boolean set intersection, the sort of thing that we saw in the CSG lesson, to get the rough geometry of each story, minus also the thickness of the walls. And then from these interior geometries of each story, you can classify them to obtain what would be the walls, what would be the ceiling, what would be the floor, based on the angle. So most things that point downwards, even when they have a slope, because you have a roof, tilted roof with eaves, are ceilings. Walls are pretty vertical, so there's a smaller tolerance, and floors are supposed to be pretty horizontal, maybe with some exceptions like for ramps and so on. So it's easy to classify surfaces based on the angle they have. He obtained pretty good results based on this. The story geometries that he computed are quite, they match the reality, and they match more or less what our intuition would say. These are some examples. Like you can look at this perspective view that you can get on Bing Maps, even where there's no 3D city data, and just to do some validation whether the pre-computed story shapes are correct or not. This is another example of more of a tower building with a parking lot in the middle, in the bottom. And so then we go to the net internal area. The net internal area is defined in a Dutch standard and considers the floor space of each story that you add them together, but there are some exceptions. Like if the height of the roof is below 1.5 meters, which can happen when you have eaves on the roof, you do not count that. And also if you have staircases, like big staircases, you also don't count that area because it's wasted because of the stairs. And so Ruland looked at the geometry he generated and tried to compute what is the net internal area and validate it with the data that is stored in the Bach dataset. For stacked buildings, he like these sort of more tower-shaped buildings, he got some pretty good results, like with values close to 0, and something a little bit higher because you have these staircases that you are not able to see from outside. But the most interesting thing happened when he looked at non-stacked buildings, so more like individual houses. And he found that there was a negative average, like this doesn't make a lot of sense. So after some experimentation, he computed the internal area total without counting, counting also the area that had a very low roof, like below 1.5 meters. And then he managed to get values very close to what the city of Rotterdam was storing in their Bach dataset, which gave a pretty strong indication that up to a certain year, I think it was like 2003, the city of Rotterdam was storing, was not computing the net internal area, it was computing the total area and taxing people based on this total area, which was larger. So this was pretty interesting result by looking at the geometry of buildings. So let's go to another example. This is from another student, Sjors Donkers. He actually built a bit on the code that Ruland made. And the idea was that you have this sort of BIM model, so architectural models made by buildings designers, like architecture firms, and they are supposed to create these BIM models in order to be able to request permits for a building's construction. But it's also become a lot more common to do this in general big projects like infrastructure projects and so on. The motivation was a bit similar, like we want to take these very detailed architectural models that are already being created by architects and designers, and we want to take advantage of them to be able to update 3D city models without having to regenerate the entire 3D city model from the beginning. Also because these BIM models have information about the interior that you cannot really get by looking only at the exterior geometry. So the goal was something like this, like this is a perspective view. On the left you have a BIM model where you have things like an exterior lamp that it was in the garden, plus a staircase, plus some furniture like a table, a trash bin, bed, and so on. And you want to go to something more like on the right, where you can look at only the walls, the windows, the doors, the roof, and so on. But as you will see in Wednesday's lesson, BIM models and 3D city models are kind of different, because BIM models are more like to what you see here on the middle and the right. So a BIM model is based on the constructive elements that you use, like things, maybe you have a concrete slab, or you have a filled-in space for a wall with insulation, you have a volume for a roof. Whereas in a 3D city model, you actually want to have surfaces, like you don't care whether something is a concrete slab or not, you care whether you have a room that can be labeled with a specific use, with a specific volume, area, and so on. So there are two different ways of looking at the world, and translating from one to the other is sometimes not so straightforward. So the methodology was something like this. You start from BIM model, which is stored in IFC. You will see that on Wednesday. And you try to map the semantics from what is typical in IFC to what is typical in a 3D city model like CityGML or CityJSON. You do a geometric transformation of every element and you try to refine it and get the semantics back when you export to a 3D city model. In terms of geometry, you need to do a few things for this, because usually with BIM models, they are in practice used only for visualization. So people don't care if the geometries don't match perfectly. So you end up with small gaps and small overlaps within the elements, which means that when you try to compute what is the volume of this, like you have done in the voxelization assignment, you are not able to compute an interior volume because the volume is not really close. So what Shores did was to actually do union of the elements and to then dilate them, like mathematical morphology, to increase their sizes a little bit to get a closed volume. This gives you what you see in D, and then you try to erode it, like to shrink the resulting volume a bit to get something closer to the original geometry. Finally, based on the geometry that you get in F, you do the same kind of semantic labeling to extract what is a roof, what is a wall, what is the ground, and so on. He obtained some pretty good results when you look at these sort of IFC models that are built from scratch, more by people in the BIM community. Yeah, so you can look at the A and B, which are the input IFC with and without the roof, so that you're able to see the interior, and C and D, which is the output CTGML that is automatically generated. It also works with some more complex examples, like multi-story houses, even big buildings. I think this was supposed to model a school. So you see classrooms. But when you start going to more complex IFC files, even the ones that were specifically generated by the BIM community, they don't work so well, because you have things like missing parts. Like usually 3D people who work with 3D modeling don't care if there are overlaps or if there are small missing pieces, as long as it looks correctly from a given viewpoint. Like in this example of a church, there's nothing in the bottom because people will not be looking at the bottom of the model. Yeah, so this was a very nice result and a sort of success, but it also highlighted that when you look at BIM models are used in practice, like generated by architecture firms, the methodology doesn't really work because there are way too many of these issues, which is something that we have been trying to work on since then. Related to that, I want to talk to you next about the master thesis of Damien Mulder. He tried to do some automatic 3D repair of building models, because you have exactly these sort of issues, like missing pieces that lead to gaps or overlapping stuff. So the idea was to use voxelization, like you did in the first assignment, because with voxelization it's easy to repair small errors, and then from the voxels you can try to reconstruct the original geometry in a bit of more sophisticated way than we did. So I think you will find this application interesting. If you look at 3D building models in practice, you have this sort of thing, like there are missing faces, like you see on the left, and there are sort of small spikes that don't really match the rest of the model, like you can see on the right, and we want to fix this automatically without any human intervention. The methodology that Damien came up with was something like this. So you have input in CTGML, you do pre-processing, like loading it into something in memory. You voxelize the model, and we will see how this is done because it's a different algorithm that is able to do some repair, and then you go back to the original output, like to the original CTGML for the output. For our voxelization, we used a method that works perfectly as long as you have a perfect model. But the aim here was actually to do some kind of repair. So The idea is that when you start shooting rays, like you see these two from the left to the right, you will hit some element like a wall, and this will switch from being in the exterior to the interior. And when you hit a wall again, you go back to the exterior, and this can be repeated any number of times. So this tells you, like walls tells you about places where you go from the exterior to the interior and vice versa. The thing is that when you have something like an overshoot that you see here, this will lead to false results, right? So it will think that you are in the interior of the building when you're not, at least for some voxels. But the key observation here is that when, in the majority of cases, you will get the correct result. And a similar thing happens with gaps. Like if you have a gap, like you see there a bit on the right, you shoot a ray, you maybe realize that you're in the interior of a building, but you never leave the interior because the ray can exit through the gap in the building. But yeah, the observation remains. Most rays that you can shoot will lead to correct results as long as the building model isn't too bad. So the idea was to not shoot one ray, but to shoot many rays in many different directions. And then you have a sort of a voting algorithm where if a voxel is deemed to be in the interior by a majority of rays, you know that you're in the interior. And if it's considered to be in the exterior by a majority of rays, you know that you are in the exterior. Like a basic example could be like shooting 6 rays in these 6 different directions, just like in 6 connectivity that we saw in the voxelization lecture. But you could also go for 18, 26, or actually any number. It doesn't need to match the directions of that you have in the voxel grid in any way. So when you try to do sort of a counting algorithm with shooting many rays, you can get good results because only a few rays will have bad results, and this goes for both overshoots and gaps. And then another interesting part was when you go from the voxelized model to the mesh that you want to get for something like a 3D city model. Here you do not just voxelize the surfaces of the voxels as we did, because this will lead you to a blocky model. As you have seen, even when you go to very small voxels, it will never look quite right. So there are many algorithms that you can use to get a better result. And an interesting one is called marching cubes, and this is used a lot in reconstruction. Maybe you might see something related to that in the 3D computer vision course, I'm not so sure. But with voxelized models, the thing that you usually do with marching cubes is that you have a 2 by 2 by 2 group of voxels that you see on the left. And for each given configuration, you define what the output mesh should look like. So for instance, if you have something like this, where you are missing one corner of the 8 voxels, you can create only a triangle that covers that, which leads to something like that on the right. And if you're missing like 2 voxels along an edge, you can imagine that the model is a bit cut in that region, and you can define like a quad or 2 triangles that cut through that part. And this leads to a much better looking result. That's one possibility. And the other typical possibility is called dual contouring. This is a bit more complex to explain, but you can imagine that in a voxel grid, you can represent also the dual, like in the Voronoi-Delaunay meaning, where you have a grid and you define a set of nodes that are in the middle of each voxel, and you can define squares and then also boxes, cuboids that go between these elements. And when you look at this and at the edge of a model, at the edge of a voxel model, you can imagine that you have the voxel model looking at something like this, like you see in the red dots with the blue dashed line. So this voxel model will only reach up to this point, and you will have these edges that are partially inside and partially outside the original model. And these edges tells you about the places where you have a sign change, like you go from interior to exterior, and these edges are very important. So if you take these dual vertices and the edges that mark the transition from interior to exterior, you can create surfaces, and you, rather than just putting these surfaces in the middle of the voxel, you can look at the original input and see where these intersect to try to guess the original points. Or you can look at the normals for the places where there was no original input in order to be able to reconstruct something better. Don't worry if you don't get this completely. It's sort of a long story to explain in this very short lesson. But the idea was to do something like this. So you have an original model with points on the interior and points on the exterior. You can imagine that these points represent voxels. When you do margin cubes, you get a sort of nicer looking shape than what you're able to get if you only output the surfaces of the voxels. But it still has these angles that are only matching like in 45 degrees, like in multiples of 45 degrees. Next, when you do dual contouring, you can do something better because you look at the intersections of these with the original model. And then there's something called pressing. That pressing basically joins multiple elements when they have exactly the same orientation. And that's how you're able to do reconstruction. Yeah, so Damien obtained some pretty nice results in terms of repair. Like in this model that you see on the left, there are two missing faces, and you're able to reconstruct what the original model looks like perfectly. Things don't work quite so well when you have multiple missing elements. Maybe this image isn't so clear, but you're actually missing this highlighted triangle and this sort of vertical one that you see, because then you will get a lot of rays that just happen to pass through both triangles at the same time. So yeah, the method works reasonably well, but it's not perfect. A model can be so bad that you cannot easily recover from that. There are also some sort of artifacts, like you see here, like this sort of staircase looks on roof eaves, or when you have the ridge of the roof, like the very, very top line of the roof, you get a series of voxels that are not really connected, which is not really ideal. Also, in some 3D city models, namely the one of Rotterdam, when you have row houses, the city of Rotterdam actually doesn't put walls between the houses, so you only have this sort of ring shape that goes around the visible part plus the bottom of the house. And yeah, it's not perfect, but Damien's algorithm can recover a bit from that. Although in some cases you can end with things like this, like non-manifold edges, which might be a problem when you try to reconstruct a mesh from that. Yeah, so finally I want to show you something quite different. So this worked a bit on the basis of point clouds rather than more the kinds of meshes from 3D city models. And it's a very nice thesis by Yixin Xu. This is okay, I think this requires a bit more of an explanation, so I will explain it as I go. People are very interested in the urban heat island effect these days because cities are tend to be, well, noticeably warmer than the surroundings, and this has bad effects in terms of health, especially now with global warming. Cities can be very hot, and this leads to deaths, like especially of very young or very old people when you have heat waves. Here you can see an example in the city of The Hague. Like you can see the redder parts represent places that are warmer, and the green parts represent places that are cooler. So when you have green space, the city is cooler than when you only have like a pavement, bricks, asphalt. This image is from the thesis of another master's thesis student that I will not be talking about today, from Ana Maria Talardime. But yeah, going back to Yishin's work, usually in order to study the urban heat island effect, you look at these weather stations. These are sort of big things, professional things. You need to have a box isolating the thermometer from the surroundings in order so that it's not hit by sunlight, and when it's hit by sunlight, you try to dissipate this heat as much as possible, so it should be more or less in the open air. It's not very clear from this picture, but there are actually some slotted vents so that the air can go through easily, and it's not too warm inside. It's supposed to be the same temperature as if you were in the shadow. So these the previous sort of professional weather stations are very bulky and expensive to install. You only have a few of these per city, or maybe one per city. Usually you have one of these wherever you have an airport. But now there's a proliferation of more small gadgets and small things. And there are personal weather stations, like this one is made by a French company called Netatmo. I actually own two of these, and I like them a lot. The interesting thing is that Netatmo gives you the option to share your data publicly. So researchers are able to use these weather stations for any kind of scientific work, including the urban heat island effect. But yeah, these are not professional things. People put them a bit in the sunlight. Some days people don't have the ideal places to put them. So even when people try their best to ensure that the weather stations are in the shadow, in a place that's at the proper height, exposed to the air, but not to currents of wind, because this can also lead to lower temperatures. Even when people try their best, the data will not be very precise. But on the other hand, you have a lot, like really a lot of these weather stations. I'm actually not showing you all of the ones here in the city of The Hague, because you need to zoom in a bit further to be able to see all of them. Rather than having a few, like a handful of professional weather stations in a city, you can have 100 or hundreds of personal weather stations. So these can be very useful in order to estimate the urban heat island effect. Unfortunately, I just took this screenshot I think a few days, like yesterday or the day before. So it's kind of cold, and you cannot see how the city is noticeably warmer than the surroundings. But yeah, when you look at the individual behavior of these personal weather stations, you will see that they tend to go up and down with some patterns. And if a certain weather station is warming, while its neighboring weather stations are not warming, you can sort of guess that it's being hit by sunlight, either directly or indirectly, like through a reflection with a window or a table or something. And based on these kinds of behavior, we can know that we can discard certain parts of the data for these kinds of research. So we are trying to remove a lot of the noise that exists in these kinds of in these kinds of data. But also, there's a lot of noise because people set up their weather station using their phone, either by putting what's their address or by using the GPS of the phone. And you know that when you use the GPS of the phone and you're indoors, you will not get a very accurate result. So the Netatmo app asks you like what's your location when you're setting it up. You just turn on the GPS, like give it a location access, and then Netatmo knows where you are, but Netatmo only knows it roughly, like within tens of meters of the real location, which is not ideal because this changes a lot the effects. So what Yixin did was to try to improve the locations of that the weather stations have according to Netatmo. And for that, you start from a given location, like the one here in red, which is provided by the API. And you generate potential locations in an area surrounding it, making sure that you are not inside a building, because these are exterior, like outdoor stations. And then you can try to guess which is the most likely location based on the behavior of the personal weather station. So yeah, given an initial point, you generate a sort of buffer around it and a grid, and you try to see what would the behavior of the weather stations would be if they were in those points. Then you try to move the station to the one that matches the closest. So yeah, you get something like this. This is an interesting example because the weather station location actually said that it was inside a building, which is impossible because it's an outdoor station. It was set up correctly based on the temperature. So Yixin created this buffer around it and a grid and a whole bunch of points, and then we try to see which location is most likely based on the behavior. In order to see what the ideal behavior of a station would be, you can start from a random location, like this is not a real one, by the way. It's in the Meckel Park in the campus. I hope you have had the chance to be there despite the pandemic. But given a location, you can generate what is called a sky view map that tells you when you look at different angles, like vertically and horizontally, you should be looking at the sky, you are looking at buildings, or you're looking at vegetation. Like here the sky is marked with blue, the buildings with gray, and the vegetation with green. And this is the key reason why you want to use a point cloud, because in the point cloud you have the vegetation. And trees can alter the results a lot, like whether you're able to see vegetation here or not. So for each of these potential locations, you generate the sky view, and then you look at the path that the sun would take, looking at the solar parameters for a given day. And then, you can see for a given location when it would be hit by the sun and when it would not be hit by the sun. You can match this behavior to the behavior that we see in the temperature change to guess the correct location. And then based on the behavior of the sun, you can also know when to discard the data or not to discard it for urban heat island results. When we compare what's the distance from the original location to the computed location, we get something like this. So most of the time it's within like 1 meter of the original location. This is a nice result because we're able to get something that is close to the original location but matches the behavior better. But we were still a bit doubtful whether this would be the case, so Yixin actually took one of these weather stations home for a few days, and he left it in a place that would be completely in the sun, well, for a few hours each day, like in a table in the middle of a garden, maybe not a very well-maintained garden, but that's where the weather station was left. And then he did the same kind of processing result for his own station. So The location given by the GPS was actually here, which is kind of interesting because this is the middle of a road and for sure it's not located in that place. The real location of the station was here, the yellow dot, and the computed location according to this methodology was the blue one here. So it's not perfect, but we're able to estimate locations better just by looking at the behavior of the weather station based on the sky view analysis. Yeah, so it was a very nice result. I hope you like it too. And I hope you're interested in pursuing maybe some of these applications, maybe in other courses or in your master thesis research. Yeah, to finalize this, I want to promote 2 courses that you might be interested in taking that are related to this. Like the first one is the GEO1014. This one is given by Giorgio and is related to energy modeling. Like what is the energy efficiency of buildings. It's done, I think, both from the data modeling side and also from the computations that you need to do. The other one is the one that I mentioned about from Clara, GEO5015, and this one is modeling wind and dispersion. Here you will be doing computational fluid dynamics. I think it's also a very cool course. And as I said before, if you're interested in doing a master thesis with applications or also with anything related to geometric modeling, you can contact me or you can contact any of the other people involved in this course. So like Hugo or Ravi, either we can help you find a topic or we can point you in the right direction if you want to do something else. So please don't hesitate to do that. Yeah, I will be uploading these. Well, actually the slides are already up in the website in case you want to have a look. And yeah, so that's it for me. I think it's the final lesson where I will be talking to you directly. Good luck with the final homework assignment of the course. Let us know if you have any issues or if you have any questions both about this lesson or the course in general. Yeah, later on I will be sending you a survey to get your opinion on the course just to help us improve for next year. So please answer that and we'll keep in touch. Yeah, if there are no questions, then I guess that's it. Thanks everyone. I hope you enjoyed the course. Bye.